Okay. Okay. The next question that we got on the menu today is asking, what is Hooke's law and the spring constant equation? So Hooke, that was a scientist. That was pretty smart way back in the day. And Hooke's law is basically all about springs. Spring. Yeah, we're talking about spring and it's not even winter. Yeah, okay. Springs, like, not the season, but, you know, like these things. If you got any mechanical pencils, they probably got springs inside. If you ever got a pogo stick, you know, there's definitely going to be a spring in there. And we know that if you push on a spring, if you compress a spring, if you, like, try this at home. If you got a mechanical pencil, if you try to push it down, well, the spring is trying to resist the amount of, it's trying to resist against you. It's pushing back on you when you push down on a spring. So, Hooke's law basically states that the force that a spring applies is proportional to its stretch or compression. Yeah, it is directly proportional to its stretch or compression. Its compression, well, if you push down on a string, they're going to push back. And for stretch, well, you ever been to like a pinball machine and like you pull out the little pinball ball pusher and it like instantly springs back in and launches a ball up there? That's an example of a spring that is stretched out and how that will also apply a force. Okay. Now, Hooke's law is true within the elastic limit. Of course, like if you really, really stretch out a string, you're going to irreversibly damage it. And of course, Hooke's law is not going to be true in that case. So Hooke's law is true in the elastic limit. The elastic limit is where you're starting to damage the spring and it's not going to act the same way. So Hooke's law is valid in the elastic limit. The elastic limit. And instead of just saying proportional, it's linearly proportional. Okay, so the equation is F equals Kx. F, that's the force. Let's say Fs, because this is for a spring. So force of spring. Whoa, let's bring it back. K, that's the spring constant. A high K value translates to a stronger spring, and low K values translate to weaker springs. So the suspension in your car, that's a pretty strong spring that's going to have a higher K value than the spring in your mechanical pencil, which probably has a very low K value. Okay, and X, this is the distance that the spring is compressed or stretched. Okay, so let's actually draw out an example. Suppose we have a wall here and we got a spring and it's actually a pinball machine and we're trying to pull out the plunger. I think that might be what it's called. And you know, let the ball fly back. Okay, so this is the start, and then we stretch out the spring like this. And the amount that it's stretched out, X, is going to be, you know, it's just going to be X. You don't necessarily need to give a number just to show like an example of this in progress. Let's make the plunger ball black so it's a little bit more clear. And we know that, well, you know, the farther you stretch it back, the more of a force it's going to apply. Now, which direction is the force? The force is always towards the center line, or towards the natural position of the spring. So in this case, Fs would be this direction. Now, if we were to compress the spring, maybe looking something like this. We would see that this distance is going to be, let's call this x1 and call this x2. And we could see here that the force would be this way. Fs, trying to return to its unstretched out natural spring position. Okay, so sometimes you'll write the Hooke's law as a negative kx or positive kx. Like, it's very confusing how sometimes you can see it written either way, but just know, like, it's good to draw out a diagram and then you can kind of know, because it depends on as well how you define your directions. So if we say forces towards the right are positive, you know, we'd want to set up our arrows. You basically just want to look at the diagram more than you look at the signs. The signs should agree with your diagram. Make your diagram before you make your signs, not the other way around, because your diagram will be more powerful, or in terms of, it's going to be more powerful in terms of telling you what's going on, because your equations only make sense with respect to the diagram. So make the diagram first. And yeah, the above solution is good. Is good. Diagrams would help. Be helpful. Okay.